Hi students. Oh, lesson 19. Only 3 more to go. Video A. We're going to do, let's see, confidence intervals for means. All right. We have to take all that theory from chapter 18, the distribution of y bar, and we have to apply it to doing a confidence interval for a mean. Running a hypothesis test for a mean. We're going to run into a big problem though real quick. The sampling distribution for the sample mean. This was lesson 18. This is the y bar model, and if certain conditions are met, then y bar will follow a normal model. Is based on knowing a key fact. In practice, we'll rarely know that key fact, and the key fact is this. Everything in lesson 18, we presumed we knew the value of sigma. Sigma is the standard deviation for the whole population. We won't know that fact, and so this video sort of describes that. Okay? As long as the conditions are met, y bar, that's the sample mean, will follow an approximate normal model with this mean. The mean of y bar is equal to the mean of y. So the mean doesn't change. If I'm looking at one observation at a time or a collection of 100 and averaging them out, the mean doesn't change. Standard deviation does change. Sigma of y bar. You had this formula. It's sigma of y over square root of n. And my experience tells me this. This is the #1 thing that students forget to do. Is if we're working with sample means, they forget to divide by root n. They just presume it's the same standard deviation. It's not. I take the original standard deviation for the population, one observation at a time, and I need to divide it by the square root of the sample size. So don't forget that part. All right, so let's say we have an example here, or I guess a couple fill in the blanks first. Here's the problem we're going to run into for the rest of the course. Lessons 19, 20, and 21. In practice, how would we ever really know the value of sigma, the standard deviation of the whole population? Look, we're going to be running tests, and we're going to be computing confidence intervals for the population mean. That's mu. Okay, so that's the last 3 lessons, is let's run a hypothesis test for mean. We don't even know the mean. That's what we're running a test for, or that's what we're computing a confidence interval for. It's a population mean. If we're not really sure about the center, how on earth would we precisely ever know the value of the spread? Okay, so we have a workaround, but with the workaround comes its own set of problems. We can handle it though. Here's the example I was thinking we were getting to. We recently read somewhere that the average credit card debt carried by college students is about $3,000, $3,173. To see if we differ, I guess here at Cecil College, we'd like to compute a 95% confidence interval for the true mean credit card debt for all Cecil College students. And it says diagram the population and the sample. So you've got some space at the bottom of the page. I'll get a blank one here so I can write a little bit bigger. Here's my population, and we're talking about the whole Cecil College. At the time of taping, I don't know what, 2,800 students, 2,500 plus, 3,000. You know, when you're watching this video, who knows how many students will be here, so we'll just say 2,800 plus students. With that whole population, all the students that attend this college, there is a mean credit card debt. It's a value that I'll never know, because I would have to interview 2,800 students. I'll never know this, right? This is unknown. I have an unknown mean. I know that figure from the newspaper or the internet, $3,100 is the average credit card debt. But at Cecil College, who knows if that holds? Here's the standard deviation. This is the standard deviation for all 2,800 students. It's also unknown. Unknown standard deviation. Think back to lesson 18 where we kept drawing all those normal models. We made a lot of assumptions and we always said, hey, I know these numbers. Like for pregnancy length. Oh, the mean is 266. Okay. and the standard deviation is 16 for all women. I guess in America, on Earth, who knows? We made a ton of assumptions about these numbers. Okay? In practice, these will be unknown, and that's why we're running tests. That's why we collect a sample. So over here, same process, whole semester. Here's my sample. In your head, it's smaller. But for the video, I need a lot of space to write, so that's why it's about the same size. Oh, let's take a sample. Did I say? I guess 50 students. Not sure why 50, but at least with 50, it's more than 30. So the normal model will kick in to gear, right? That theory that we learned. Once I interview my 50 students, survey them, I can calculate the sample mean. I'll call it Y bar. The symbols are different, and they're important. This is the sample mean. This will be a known value. Once, I don't know what it is, because I'm just diagramming what's going to happen, but this will be a known value, once data is collected. Think of that data. I'll have a list of 50 students, and next to their names, probably anonymous, right? I'll have a list of 50 credit card debts, and I can add them up, divide by 50. That number will be known. I can do the same thing with the standard deviation, S. S will also be a known value. And to save it from, put an arrow here, both of those. Once I collect my data, I'll know those numbers. All right? Back from lesson 18, of course, if I threw back those 50 students and randomly selected 50 more, these numbers would change, right? They will be our best guess. If I wanted my best guess for the sample mean, or excuse me, if I wanted my best guess for the population mean, after I collect data, I would use that number. And similarly, if somebody said, hey, Coop, what's your best guess for the standard deviation for the whole school? Then I would say, well, let me just go to my data that I collected, and I'll tell you my number from here. It's not right, but it should be a good estimate. Okay? Here's the thing. In lesson 18, the sampling distribution for the sample mean for Y bar is based on knowing these two numbers. In practice, we won't. Okay, sampling distribution for Y bar is based on knowing mu and sigma. And so understand what's happening here, right? We built a theoretical model back in the last lesson, and we made a lot of assumptions. Now we're going to the real world here on the left-hand side. Okay, so if we flip the page, that's sort of the big problem that we need to address. All right, let me clean this up. The big problem. We're going to perform inference on our population, right? When we do a hypothesis test, we're testing for a population parameter, like a mean or a proportion, based on our data, based on our collected sample, and based on our sample statistics. We only have a best guess for the population standard deviation. And like I referred to, our best guess for the population standard deviation, sigma, is the sample standard deviation, which is S. So, since I need this, but I can't get it, the solution is use this, the best guess. That opens up more problems. I think we solved our problem, but we didn't. So, if we replace the value of sigma with S in our sampling distribution, here's the kicker. The sample mean Y bar no longer follows an approximate normal distribution. And therefore, everything we learned in 18, which is good stuff, about normal models is not going to apply for the rest of the course book. 19, 20, and 21, all this inference about sample means or population means is we have to fix the problem. Okay? So, in lesson 18, here's a good way I started thinking about it. All those normal models, we were working in a sterilized environment. We made a lot of presumptions. Oh, I know the values of the population parameters. I knew the population mean, mu. I knew the population standard deviation, sigma. When we move to the real world, which is what statistics is all about, when working with sample data, we won't know those values. So we must approximate them with the sample statistics, y bar and s. When we do this, we're going to need a new model to serve as the basis for our confidence intervals and our hypothesis tests. Okay? So, the big solution. When we collect our sample data, we're going to work with the standard error of the sample mean rather than the standard deviation of the sample mean. And so we can lay this out at the bottom of that page. Mine's side by side. Looks like yours is up and down. But in the real world, with real data, we have to use the standard error. We did this for proportions, by the way, with all that p hat stuff instead of p. Here's for the mean. With standard error, you could call this SE for standard error of y bar. And what's that going to equal? It's S over square root of n. I'll know this after I collect my data so I can calculate its values. And this one comes from collected data. Comes from the collected data. This is lessons 19, 20, 21. Ideally, I would like to live in the theoretical sterilized world where I knew every fact about every population, every population mean and every population standard deviation. And if that's the case, then I could calculate the standard deviation. And so the standard deviation of y bar, you could call it sigma. I just put SD and SE. This is sigma over root n. We don't live in this theoretical sterilized world, right? And I guess, I don't know. This comes from knowing the value of sigma, which we won't. So, we'll flip the page. There's an interesting story as to how this was discovered and sort of, when we do this, we need a new model. Normal model goes out the door. And so let's learn who discovered this and what the fix was. All right, it was a guy by the name of Gossett. Interesting short little story here. So let me get my notes because maybe I forgot the story. The statistician who was credited with discovering the new model we will use for working with means was named William Gossett. To be clear, why do we need the new model? It's because I'm using S instead of sigma. And so normal model won't apply to what we're going to be doing. He made his important discovery back in the very early 1900s. So this model we're going to learn about is really only about 100 years old. So it's not ancient history. He made his discoveries back then. It wasn't without controversy. Interesting story. He worked for Guinness over in Ireland, which, as you probably know, or maybe not, but Guinness is a brewery. And he had a great job. He has a job I think I would like to have. He was the beer tester guy, quality control at a brewery, and he was testing beer using statistical methods. I'm not sure what kind of tests, maybe for alcohol content, maybe for taste, maybe for clarity, who knows what. Essentially what was happening is that the folks working back in the brewery were sending samples of beer to be tested before it went out to market, and Gossett kept, well, rejecting the samples. And the brewers were getting upset with this statistician guy because he said the beer is just fine, we need to sell this, make some profits, right? He tested the beer using statistical methods, Gossett did. He was frequently making errors because he was using the wrong model. He was using the normal model. Gossett discovered, especially when working with small sample sizes, and if you're testing beer, you're probably going to be using pretty small sample sizes. One, because of the alcohol. Two, because if you keep testing the beer, you can't sell it. You're in the business of making money. So he was using the normal model inappropriately because he was substituting S in for sigma, because that's all he had. Right? All he had was a sample standard deviation. So here was his discovery. Rather, the model is also bell-shaped. And in fact, if I drew the new model and I said, what model is it? You'd say normal instantaneously, and I don't blame you. The model was bell-shaped, but there is a bit more area in the tails. Essentially, take your normal model and squish it down and push a little bit of the area out to the tails. So compared to standard normal, more area in the tails. When using the new model, and here's why Gossett was making his mistakes, confidence intervals, they needed to be a little bit wider on purpose, and the new model helped with that. So when using this new model, confidence intervals tend to be a little bit wider on purpose. And just think about that. If your intervals are a little bit wider on purpose, aren't you less likely to reject a beer as saying like, oh, it's too high in alcohol content or it's not clear enough? Because if the intervals are a little bit wider, you're going to hit that key value just because it's wider, right? So that's what the new model does. Take that to hypothesis testing. When using this new model, hypothesis tests will generate p-values that are a little bit larger on purpose. If your p-values are a little bit larger, isn't it harder to reject the null? Isn't it harder to reject that beer and the beer goes out to market? So we're going to make our intervals a little bit wider on purpose. We're going to make our p-values a little bit larger on purpose. Guinness, the beer company, felt that the statistical discovery was a trade secret. Should be kept in-house, top secret, nobody knows about it but us. Gossett convinced management that the discovery would be of no practical use to the competing breweries. So there was a little bit of controversy. Do we keep this in-house? Should we allow Gossett to publish it? Gossett was finally allowed to publish it. He had to do it under a pseudonym. He couldn't sign his name because that way it'd be linked back to Guinness. So he signed it student. Therefore, this noteworthy achievement doesn't carry his name. It's not Gossett's distribution, but we all know it's his. The Gossett's distribution is called the student's team. Or you could say model, right? Like normal model, normal distribution, those are synonymous. So this was his discovery. Does not carry his name, carries the name student, and it's stuck. So that's how we describe it. Down at the bottom of the page, we've made this as easy as we possibly can for students. So pay attention and you'll never make a mistake. When you're performing inference on proportions, we'll use the standard normal model. That stuff's history though. We're done with standard normal. At least in the videos. You're still responsible, of course, for knowing it. But that was lessons 14 to 17. Now, to close out the course, we're performing inference on means. You have to use the student's T model. And we're going to do the same thing. In this lesson, we'll do confidence intervals. You just have to use this model. And Kim Shepard's going to show you how to do it. And in lesson 20, we'll do hypothesis tests. And you just have to use the student's T model. Okay? So, thanks for watching the video. Kim will be back to tell you all about the student's T distribution, and we'll see you in class.